Hey guys, it's your freaking favorite medical channel, Medicosis Perfectionalis, the Rolls Royce of medical education. Let's continue our physiology playlist. In the previous video, I have talked about the action potential, but now it's time for the ionic basis of the action potential. With that said, now let's get started. This is my physiology playlist. Please watch these videos in order. Today is video number 47. Let's start by answering the question of the previous video. Alright, here is a source of electricity, and here's a stimulus, and here's the recording electrode. The distance between these 2 points is about 70 millimeters. The recording electrode recorded something that looks like that, and the duration between A and B was about 7 milliseconds. The question is, what's the likely type of this nerve fiber? Do you think it's type A fibers, type B fibers, type C, or you have no idea what the flip is? Let me answer this for you. Okay, what's the distance between A and B? This is called the latent period, which is the period between giving the electrical stimulus and noticing the response. What is the latent period in infectious diseases? It's the period between the entry of the organism to my body and me starting to show some freaking symptoms. Same flipping concept. Whenever you have a distance and time, what's the third aspect? Oh, speed. I'm talking about velocity, not what you're smoking. That was a neuropharmacology joke. Velocity equals distance over time. What's the distance here? About 70, all right? 70 millimeters over 7 milliseconds. And you get what? You get 10. The measuring unit is millimeters over milliseconds. You can cancel the milli with the milli and you end up with 10 meters per second. Now, if you remember your physiology, which nerve fiber type had a velocity of 10 meters per second? And the answer is type B fibers, because the conductance velocity in type A was 100 meters per second, in type B it's 10, in type C it's just 1. For the physics nerd in the comment section, what's the difference between speed and velocity? Because there actually is a difference. Let's review the nuggets of medicine. Nugget number 1. Why do we need the action potential? Because the action potential is life. The nerve impulse is unidirectional inside your body. We call this orthodromic. Nugget number 3. The nerve impulse starts at the axon hillock, the most excitable part of the axon. Nugget number 4. During rest, the inside of the membrane is negative, but upon activation, aka depolarization, more accurately reversal of polarity, the inside of the membrane becomes more positive. Nugget number 5. Local anesthetics will affect type C fibers before B, before type A. Why is this? Because C is the thinnest type of fiber. It's also unmyelinated. To learn more about local anesthetics, check out my anesthesiology playlist here on YouTube. Nugget number 6. You will be affected by hypoxia the most if you are very active, metabolically speaking, and far away from the artery, anatomically speaking. And that's why type A fibers are the most vulnerable to hypoxia. So when it comes to susceptibility to pressure or to hypoxia, type A is the most susceptible. When it comes to susceptibility to local anesthetics, type C is the most susceptible. Nugget number 8, chronaxia. What is chronaxia? The word chrono means time. That's why we say chronic diseases. So chronaxia is the time needed by a current whose intensity is double the rebase to excite the nerve. The greater the nerve excitability, the shorter the chronaxia. The chronaxia of nerve fibers is less than chronaxia of muscle fibers. Well, no kidding, because nerve fibers are more excitable than muscle fibers, electrically speaking. Forms of membrane potential. This is the most important slide. During rest, your membrane is undergoing resting membrane potential. Upon stimulation, well, it depends. If you give me a robust, adequate threshold, I'll give you a robust action potential. But if you treat me with no respect, I will treat you with no respect. Local response. Almost nothing. But this is robust. This is the secret sauce. During rest, the membrane is resting, no duh, and the inside of the membrane is negative. Why? Because positive is leaving, potassium efflux. Then action potential happens. Now sodium is rushing in through the fast voltage-gated sodium channels. Sodium comes in, sodium is positive, the inside of the membrane will become more positive. Let me ask you a question. At this moment, when sodium has entered, do you think sodium is more prevalent in the extracellular fluid or in the intracellular fluid? The answer is it is still more prevalent in the extracellular fluid. This is just a drop in an ocean. I mean, if you fart in the wind, will anyone smell it 2 miles away? The answer is no. If you pee in an ocean, will it turn amber yellow? Absolutely not, because it's not significant. Same thing here. When sodium has entered, we have a reversal of polarity, but not reversal of concentration. Still, sodium is more abundant outside and potassium is more abundant inside. Oh, please don't urinate in an ocean. This is how Egyptians spread their cercaria all over the place. They got all kinds of schistosoma hematobium action going. And on your standardized exam, if the question starts with an Egyptian patient, you know they're asking about schistosomiasis, or at the very least, hepatitis C. Oh, by the way, the cercaria was spreading in fresh water and not in an ocean because the ocean has salty water, and salty water will probably dehydrate and kill the freaking cercaria, but that's a story for another time. Next, repolarization. Oh, I know repolarization. It's potassium. Shut up. First, you have to stop and close the sodium channels. All right, stop it. And then you open the potassium channels. All right, potassium is leaving. The positive is leaving the inside more negative. But because these potassium channels are slow at opening and slow at closing, you will overshoot. Instead of reaching -90, you will overshoot to -100. Until some beautiful inward rectifying potassium channels open, letting the potassium in. Next nugget, what caused the resting membrane potential? Selective permeability and the sodium-potassium pump. Selective permeability in one sentence, potassium efflux. Thank you. The polarized state is caused by the potassium efflux. Polarized attitude is caused by the potassium abandoning the cell. Potassium is leaving during rest. Some teeny tiny amount of sodium is entering. Which one is more important? Potassium is more important. How did you know this? Nernst equation. The resting membrane potential depends on the selective permeability and the sodium-potassium ATPase. Which one is more important? Selective permeability. How did you know? Goldman's equation. We have talked about these two before. Sodium problems, you get CNS problems. Kalium problems, you will suffer from cardiac problems. With hyponatremia or hypernatremia, you get mental status abnormalities. But with hypokalemia or hyperkalemia, you get arrhythmia and muscle problems. Nugget number 15, the rule of fours. Wow, look at this. The normal sodium in the plasma, normal chloride, etc. Everything has a 4. Polarized state is caused by the potassium. So who is the hero of the resting membrane potential? Potassium. Who is the hero of depolarization? Sodium. Sodium is abundant outside the cell. Potassium is more abundant inside the cell. And this will not change whether you're talking about repolarization, hyperpolarization, depolarization. It doesn't freaking matter. Because during depolarization, there is only a reversal of polarity, but there is no reversal of concentration. What do you mean by reversal of polarity? The inside of the membrane is becoming more positive instead of more negative. What do you mean by no reversal of concentration? I mean, still sodium is more abundant in the extracellular fluid and potassium is still more abundant in the intracellular fluid. If you pee in an ocean, it's not gonna turn yellow. Who's responsible for the resting membrane potential? Potassium is leaving. Who is responsible for depolarization? Sodium influx. Who is responsible for repolarization? Potassium efflux. Who is responsible for hyperpolarization? Potassium efflux. Who is responsible for the return to the baseline? The inward rectifying leaky potassium channels. The ascending limb is depolarization, the descending is the repolarization, and this is the hyperpolarization when you overshoot. Which one lasts longer? Hyperpolarization, and this is a very important point. That's why, by the way, we call the inward rectifying potassium channel inward rectifying, although it also allows the potassium to leave, so we should call it outward rectifying. But wait a second, hyperpolarization takes more. So if you sit there and contemplate and look at this beautiful channel, you will find that most of the time it's letting the potassium in. That's why we call it inward rectifying. But for the rest of the time, which is not so long, it's letting the potassium out. Sodium channels are fast. They are fast at opening and fast at closing, but the potassium channels are slow. They are slow at opening, slow at closing. Slow at opening. That's why the descending limb, the potassium limb, happened after the sodium limb. Slow at closing. That's why they overshoot. Alright, this is going up and this is going up. What's the difference? This is slow depolarization and this is fast. No kidding. What's the difference? Here you have opening of some sodium channels, some sodium efflux. But here, all of your sodium channels are open and sodium will rush into the neuron. What's the magnitude of the action potential? From -90 to 0 is 90. And then you add 35, so 90 plus 35, you get 125. That's the magnitude. Millivolts, not volts. Volt is gonna kill you. What's the tipping point? It's called the firing level, beyond which, boom, so fast, baby. Rapid depolarization. So depolarization has a slow phase and a fast phase. Similarly, repolarization has a rapid phase and a slow phase. There is also hyperpolarization because we are slow at closing. Between the stimulus and the response is the latent period. This is polarized. This is reversal of polarity. Hashtag depolarization. Pause and review and use your imagination. Let's talk about the sodium channel alone, as if the potassium channel did not exist. Alright, sodium channel, when will you get started? I'll get started here at the tipping point, the firing level. Alright, and I will go up right here. Who helped you open more sodium channels? A positive feedback loop. So in the beginning, some sodium channels open, and then they helped others. They helped their brothers. Open more sodium channels, and the opening of these sodium channels is gonna help open more sodium channels until boom, it's the spike, it's the surge. Remember the LH surge in ovulation? Same flipping concept, it's called positive feedback loop. But don't forget that most of the feedback in your body is negative feedback, not positive feedback. Positive feedback is rare, physiologically speaking. As you see, sodium channels are fast at opening and fast at closing. We're done. Sodium channels are more voltage sensitive compared to potassium channels. And therefore, sodium channels are activated at a more negative membrane potential compared to the potassium. So if these started at negative 90, potassium will start at about negative 80. So sodium started at an earlier period because it's more sensitive. Let's talk about the potassium alone. It is slow at opening and slow at closing, and it does not touch the positive 35. And that's why depolarization is the sodium's job. Let's put the sodium and the potassium graphs together. Sodium graph alone, rapid and rapid. Up and down, quickly. But look at the potassium. Slow at opening and slow at closing. Why is this? Because sodium channel has 2 gates, but potassium channel has just 1 gate. Pause and review. What kind of potassium channels do we have in the neurons? We have 2 types. Leaky inward rectifying potassium channels and the slow-acting voltage-gated potassium channels. These are non-gated, but these are gated, and the gate will open by electricity. That's why we call it voltage-gated. As opposed to what? As opposed to ligand-gated. Even though they are called leaky inward, their job is to let the potassium in and out. Let it out, responsible for the resting membrane potential. Let it in, responsible for the return from the hyper to the resting. Since most of the time the channel is busy here, allowing the potassium in, we call it the inward rectifying. But this is the same channel that let the potassium out as well. The voltage-gated one is responsible for repolarization and hyper. The voltage-gated potassium channels are slow. Slow at opening, slow at closing. Slow at opening. That's why repolarization starts after depolarization. That's why repolarization lasts longer than depolarization. Slow at closing. And that's why we overshoot. Sodium channels versus potassium channels. Why are sodium channels faster? Because they have 2 gates. Potassium channels are slower because they have 1 gate. It's like the difference between the revolving door and the good old door. If you have a big skyscraper, should you prefer this one or this one? Of course this one. It lets in more people in a shorter period of time. You know why? Because it has more than 1 gate. Duh! So in the beginning, everyone is closed. I'll give you 1 second because this one has 2 gates. It will give me a 45-degree rotation, and this will give me 45-degree rotation. And then after another second, 45-degree rotation, 45-degree rotation. Look at this. This sodium channel, since it has 2 gates, has opened and closed, and we're done in just 2 seconds. But by the time the sodium channel has opened and closed, the potassium channel has just opened. If you want it to close, give it another 2 seconds. And that's why sodium channels are faster than potassium channels. Look at that, just 2 seconds, but this one took 4 seconds. Voltage-gated sodium channels has 2 gates responsible for depolarization. So, during rest, the outer gate is closed. Alright, where's the inner gate? It's open here, but we don't care about it. Alright, let's open the outer gate. Alright, sodium is gonna rush in, and the membrane is gonna be active. Hashtag depolarization. Oh, so this is the gate that's responsible for activation? Sure, let's call it the activation gate. So the activation gate is the same as the outer gate. Sodium has rushed in, and then, after depolarization is done, let's stop it and close the inner gate. And in this period, the membrane will become inactive again. And that's why the inner gate is called the inactivation gate. You want a mnemonic? The inner gate is the inactivation gate. I got this from my professor. It's not mine. How about the potassium channel? It just has one gate. So we don't say activation, inactivation because it doesn't matter. Some books will refer to it as just one activation gate with no inactivation gate, but who cares? The Ionic basis. I love this chart. We'll divide the action potential into 1, 2, 3, 4, 5, and 6 phases. All right, 1 is the resting membrane potential. What's happening during rest? Sodium channel closed. Potassium channel closed. What kind of potassium channel are you talking about? I'm only talking about the voltage gated potassium channel. Because if you're talking about the leaky inward rectifying, that one is always leaky. It's always open. And during rest, it is letting potassium out of the cell. We don't care about that one right now. We're just talking about the voltage gated potassium channel. Okay, all of them are closed. Phase number 2, the slow depolarization phase. Some sodium channels have opened, right? Opened by which gate? The outer gate, the activation gate. How about the potassium ones? They are slow at opening. They are still sleeping. Next, a positive feedback loop will help us open all of the sodium channels. So during phase 3, the rapid depolarization, all of the sodium channels are open. Opened by which gate? By the outer activation gate. Potassium channels have started to wake up. Some of them have opened to let the potassium out until we reach the tipping point here and depolarization is gone. Let's start repolarization. All right, sodium will close. By which gate? The inner gate, the inactivation gate. And now the membrane will become inactive. Potassium channels, all of them are open, letting the potassium to get out of the cell. That's why you go from positive 35 to negative 90 or negative 100, because when the positive is leaving, you're becoming more negative inside. Phase 5 is hyperpolarization, the overshoot. Of course, the hyperpolarization is not sodium's responsibility. Sodium channels are closed. By which gate? The inner gate, the inactivation gate. How about potassiums? They started closing. Don't forget, at this moment, the leaky potassium channels will start to let potassium in until you reach the resting membrane potential where all of them are closed. What's the difference between 5 and 6? In 5, sodium was closed by the inner inactivated gate, but here we're closing by the outer gate. Hey Medicosis, how do I remember that during rest, the sodium channel is closed by an outer gate, but the potassium gate is on the inside? Easy. Where is the sodium normally? Sodium is more abundant in the extracellular fluid. Excellent. That's why it makes sense to put the gate closer to the sodium, closer to the outside. But where is potassium normally? Oh, potassium is more abundant inside. That's why you put the gate on the inside. It just looks sexier. Alright, we're done with the action potential. Let's go back to square one because the party is over. Who's gonna do this? The sodium-potassium ATPase pump is gonna re-establish the gradient. Dish the sodium out, dish the potassium in. The action potential follows the all or none law. What does that mean? It means there is no sorta kinda ish, cause ish is a wish. I'm either fully excited or not. There is no 10% excited or 50% excited. I don't play these games. If you give me a robust stimulus, a threshold, I will give you my maximal excitability, 100%. But if you give me something that's below threshold, I will not respond at all. To borrow a phrase from my hero, Dr. Thomas Sowell, there are no half-baked notions with the action potential. It's all or none. I'm either up or down. I don't dance on the stairs. Okay, Medicosis, I'll give you sub-threshold. What will you do? I'm not gonna be excited at all. Okay, Medicosis, I'll give you threshold. I'll give you 100% response, 100% excitability. Okay, Medicosis, I'll give you supra-threshold. I'll still give you the same 100%. It's either all or none. Absolute refractory period versus relative refractory period. What the flip is that? It's a refractory period. So the definition is, it's a period, well, no duh, of time during which a second action potential cannot occur because I'm busy in the first action potential. Right, I'm busy. Okay, stop it. You mean I cannot excite you for the second time? Nope, you have to wait, no matter how strong the stimulus is. Where does the absolute refractory period extend? It extends from the firing level, the beginning, to the end of the early part of repolarization. So it's the depolarization phase and the first 1/3 of the descending limb. Why does this happen? Because inactivation of the sodium channels. When these gates close, you cannot open them instantaneously because there's something called inertia in physics. They have to wait until they're able to open again. So you have to wait. How about relative refractory period? Well, I'm still refractory period. So I'm a period of time during which the second action potential is hard. Unless you give me something supranormal, something stronger than usual. Only then I will start listening to you. And this starts from the end of the absolute refractory period to the end of the hyperposition before you reach the resting membrane. Why does this happen? Because some sodium channels have returned to their resting state. Oh, I'm ready to be opened again. So we have talked about the action potential. In the next video, we'll talk about the local response when you give a subthreshold. Some clinical pearls for the pros. Antiarrhythmics, baby. We have 4 classes of antiarrhythmics. Class 1, sodium channel blockers, beta blockers, potassium channel blockers, calcium channel blockers. How do I remember them? Smoke bitter pot in California. Wiser words have never been uttered. The atrial and ventricular muscles of the heart also have depolarization, also caused by sodium influx. But what if my heart is beating too fast? Give me a drug that blocks the sodium channels. Hashtag sodium channel blockers. You see the sodium channel? It has an outer, activated gate, and inner, inactivated gate. During rest, I'm closed by the outer. Upon depolarization, I open the outer, and then I close by the inactivated. The class 1 antiarrhythmics, aka the sodium channel blockers, are divided into 3 classes of medications. 1A, 1B, and 1C. Where do 1A work? Well, 1A inhibits here. It inhibits the activation of the sodium channels. It inhibits the opening of the outer activated gate. How about 1B? 1B inhibits this. What do you mean? I will keep it closed. You mean it's not going to be able to open? Nope. You stay here, doofus. You stay here. Stand still. But sodium is not going to be able to enter. That's my job, doofus. This is my mission. And 1C are all over the place. They don't care. Your nerve has a refractory period. Same thing with your heart muscles. It has refractory periods, and we divide them into absolute refractory period and relative refractory period. Sometimes we call the absolute effective refractory period. The difference between the action potential in the nerve and in the cardiac muscles is this beautiful plateau. I can make an entire video just about the plateau because it's so significant. If you remember my anesthesiology playlist, I've told you about local anesthetics. How do they work? They inhibit the voltage-gated sodium channels. They let the channels shut down, and then they prevent the gate from opening again. So sodium is not going to be able to enter the nerve. No excitability, hashtag no pain sensation. If that's the local anesthetic medication, it will clamp the channel here in the closed inactivated state. Hey, inner gate, remain closed please. Never open it. Never let the sodium in. If you want to learn more about antiarrhythmics, anti-anginal, antihypertensives, antihyperlipidemics, diuretics, and digoxin, check out my cardiac pharmacology course on my website medicosisperfectionalis.com. I also have an autonomic pharmacology course on the same website. Thank you for watching. Please subscribe, hit the bell, and click on the join button. You can support me here or here. Go to my website to download my courses. Thank you for watching. As always, be safe, stay happy, study hard. This is Medicosis Perfectionalis, where medicine makes perfect sense.